Okay, all right. It looks like there's a little bit of a delay, so I'm gonna wait to make sure. Okay. I want to make sure people can hear me. Okay, and I am viewing YouTube chat. So I want confirmation that people can hear me. I'm gonna wait a little bit. I just want to see how many people are going to be here, and making sure that everyone who wants to be here will have the chance to do so. Um, and I'll be following along. Make myself a little smaller. Okay, hopefully that is all fine. All right, Tommy, that was great to hear. Okay, I am going to wait until 4:05, and then at 4:05, I will start. I guess it'll be 4:05 for me. I know there's probably a little bit of a delay. I just want to make sure that everyone who wants to see it will have the chance to do so. Hello, Yuna. You're from the Discord. I guess there's a lot of Discords, but it's great to see everyone here. This is really exciting. I hope that you guys enjoy it, and I hope that yeah, that this can be an experience that we can communicate me through talking here, and you guys through YouTube chat. um, so I'll just be waiting just a little bit more until I officially begin. Um, that is awesome. This looks like we have 7 people here. That is really cool. Yeah. So like I said, I'm just gonna give it a little bit more time, and then we will be ready to go. And all right, it looks like it is 5:05. Okay. So, hello everyone. If you don't know, my name is Mark, and this is my math YouTube channel called, appropriately, Mark Does Math. So this is going to be kind of like a series of live streams, hopefully, where I talk about a concept called irrationality. And, well, like specifically, like, what does it mean for a number to be irrational, and how do we know it? So this is going to be kind of hopefully an accessible entry into this. This will involve proofs, and so that will make things complicated in that sense, but my hope is that you wouldn't have had to take calculus to necessarily understand these things, but to be able to maybe have a sense of how to do like algebraic manipulations and stuff like that. As always, if there are questions, I would recommend I would recommend typing in the YouTube chat. I have it on another device, so I will be able to see it. There will be a little bit of a delay. That's just how streams work, or at least that's how my device capabilities are currently. But I will try to attend to these questions as best as I can. All right, so without further ado, let's begin. So, I see a question from Tommy. Yes, that will. I believe I know who you're referring to, and to the person who is worried about that, I believe that you will be just fine. But again, if you have any questions, please feel free to ask. So let's start with the integers, which are nicely denoted as this set Z. And you can think of integers, they're like whole numbers, but they can also be negative. So it's a set of 0, plus or minus 1, plus or minus 2, plus or minus 2, and so on. And the integers are like an infinite set. And so there's like a more rigorous way to define it, but I'm going to just use these intuitive ideas to get this point. And then the second thing I'm going to assume is that, real numbers are. And specifically, I'm differentiating between real numbers and complex numbers, right? Where complex numbers have some sort of like square roots of negative numbers and stuff like that. But that is totally beyond the scope of this video. I'm just focusing on things within the real numbers for now. Maybe in future videos I will get into that. So, what is a rational number? Right. Rational. So, a rational number is a member of the real numbers. It's a subset. And we call the subset Q, kind of with this nice symbol. And it is the set as follows. We have B divided by A, such that A and B are integers. So hopefully everyone can see that right here. Oh my goodness. So basically we have a rational number if we can make some sort of ratio with them. If we do B divided by A, that this can be some sort of commonly understood ratio. And specifically, it's always possible for A and B to be integers for a number to be rational. Now, often you'll kind of see this definition, maybe the elementary school, middle school definition, which is completely valid, would say that if you have some sort of decimal, that irrationality would mean it's like non-repeating, non-terminating. So some decimal like 1, 0, 1, 1, 0, 1, 1, 1, 0, right, and so on and so forth. And the idea is that this kind of pattern continues, but it's a non-repeating pattern. And so this is an irrational number. Or something like pi 3.1415926, and so on and so on and so forth. But the thing is that these kinds of explanations, while it's very intuitive, and I would say that it's very helpful, they can be kind of unsatisfying. And here's the reason why. Well, there's multiple reasons. But let's say we have a number line. Let's say this is like 0, and this is 1, and this is -1. Sorry, reading the comments. I know pi up to 3.1. I love that. And we always just keep continuing to work on it. So we think about rational numbers between 0 and 1. And we can find 1/2. We can find 1/4 in between that. We can keep going, right? We have 1/8. And of course this is a pattern, right? I could say like this is 1/102, for example. But the idea is we can keep on zooming in to this range, and we could zoom into any range, and we could get more specific on kind of the rational numbers that we want to find. And so you might be thinking, like, well, can we find numbers on this number line that are irrational? Of course, if you've taken a sort of math course, you've probably heard about irrational numbers. You probably know examples. For example, pi, which is, like I said, it's to the right here. Pi is somewhere over here. But you might be thinking, like, how do we even know, like, that exists? And in fact, I'll admit, when I first learned about pi, I think I was in like 5th grade, and my teacher was explaining that, there's no last digit of pi, and that computers are still, like, calculating new digits. And I really believed that eventually, right, we were going to have a computer, and they were going to find either the last digit of pi or some repeating digits. And, what I didn't realize at the time was that, of course, over like 100 years before, maybe 200 years even, that someone had, like, proven, using calculus, that pi is irrational. So we're not going to prove that pi is irrational today, although I would really hope to at some point, because I think that's a really interesting idea. But the point is that there are gaps in these rational numbers, even though it doesn't look that way. Even though it seems, because they're an infinite amount, an uncountably infinite amount of rational numbers, even just between 0 and 1 alone, that there are still these gaps that are in between. And so today, my end goal is to show that the square root of 2 is not a rational number. And this little symbol here is just the symbol for saying that it's not in something, right? So the square root of 2 is not a member of this set, right? The square root of 2 cannot be written as a fraction, a over b, for b and a being integers, or b over a, in this case. So how do we do this? Well, there's going to be a lot of steps, and I want to kind of think about this from a number theory background, using kind of the generally accepted axioms of number theory, and seeing if we can start from there, and eventually getting to this point. So I have a general outline of what I want to do. I believe that we have finished the first of these. That is not what I wanted. Oh, that is... Oh, no. That is not what I wanted. Okay. Our motivation part is complete, and now we'll move on. So the first thing I want to show is this, and maybe I'll call it Theorem One. This is a little light. I want a little darker color. Okay, I'll just keep it in black for now. Can I make like the pen size? Really? Okay. That doesn't matter. So Theorem 1 will be the following. So we're going to let A and B be members, right? So this sign means that A and B are both members of the integers. Then there exists Q and R in the integers such that A equals BQ plus R, and 0 is less than or equal to R, which is less than B. So essentially, we are given the integers A and B. We want to find integers Q and R such that A equals BQ, B times Q, right, plus R, and 0 is less than or equal to R, which itself is less than B. And this is called the division algorithm. And you might be looking at this and thinking, Mark, this doesn't have anything to do with division. And so the way we could think about this is if we have this equation right here, we can divide both sides by B. So we have A divided by B is equal to Q plus R over B, and 0 is less than or equal to R over B, which itself is less than 1, right? So if you have ever done long division, right, you would get a remainder. And the idea is that the remainder is too small to go into the number that you're dividing by. And so that's why we have the remainder. So in this proof, I want to show basically the existence of a remainder that is non-negative, but is also less than B. Right? This theorem says that it is possible. But how can we go about showing that it's possible? Well, let's get started. So this is the proof. So to do this, we are going to create a set. So create a set S. What is S? You might be asking. S is the following. It's elements of the form A minus BX such that, this vertical line is such that A minus BX is non-negative. So essentially what I've made here is, if you think about it, if X were to be Q, I would have isolated for R. So I'm kind of showing that there exists, I want to show, in a sense, that there kind of exists a positive R. But we're going to get to that. The first thing is, are there any elements of S, right? A and B are given. So can we find an integer, X? Right, so let X be an integer. That's an important specification. Okay, so if we let X be an integer, can we find an integer X such that A minus BX is greater than or equal to 0? So let's see. If X is equal to the negative times the absolute value of A, then we have the following. A minus BX is equal to A plus B times absolute value of A. Yes, okay. And so we want to show is this greater than or equal to 0? And we don't know this yet, but if this is true, right, then we'd show that there exists a value x such that this set is non-empty. Okay, so one thing I realized I forgot to mention, in the premise of this theorem, we want to assume that b is greater than 0. And the reasoning behind that is if b equals 0, then a over b doesn't make sense because you can't divide by 0. And we're going to generalize it. B could be negative, but the thing is that we can always generalize it so b is positive, because a divided by b is either going to be positive or negative. If it's positive, then a and b can both be positive. And if it's negative, we're going to let the a be negative. So we're kind of just going to break it down just in the case where b is positive. So, and this is kind of a side note, I'll denote it a different color here. We have b, which is greater than 0. So b is greater than or equal to 1, right? And we see that because b is an integer. So every integer that must be greater than 0, it is at least 1, because it can't be 0, but it's any integer greater than that. And 1 is the smallest integer greater than 0. And so we can multiply both sides by absolute value of a. And then we see that absolute value of a must be greater than or equal to negative a, right? And this is true regardless of whether or not a is positive or negative, right? Because if a is positive, then absolute value of a will be positive and negative a will be negative. If a is negative, then this will be positive. This here will also be positive because a negative times a negative is a positive. And thus we'll have an equality. So we know that this here is true. And so by the transitive property, we have that b times absolute value of a is greater than or equal to negative a. And then we can add a on both sides. So b times absolute value of a plus a is greater than or equal to 0. Well, hang on, this is the same thing. B times absolute value of a plus a greater than or equal to 0. B times absolute value of a plus a. So we have shown this. This is true, and we can take away the question mark. So, thus S is non-empty. Therefore, we have a set now that is non-empty, that only contains positive elements. And so we use something called the well-ordering property, which basically states that if you have a set of integers, because S is only going to have integers, that only has positive elements, or non-negative in this case, because one of them could be 0, that there will be a least element, right? At the very least, it could be 0, but it might be greater. And so I'll write this down here. It's the well-ordering property. Which basically means that S has a least element. So we know there exists a least element. Let's call it R. And you might be thinking, why call it R? Well, we're going to show that this least element ends up being the remainder. But we're going to get to that. Thus, for some x, r is equal to a minus bx. And thus, we can call this x we can call it q. So thus, we've kind of shown the first part, right? Thus, there exists a q and an r in the integers, such that a minus bq is equal to r. So a is equal to bq plus r, right? Because we just add bq on both sides. And we know that r is positive because r is a member of S. So, and r is non-negative, right? Because we can still let the remainder be 0. Sometimes the division will turn out to be an integer. So this is really nice. But we do want to show that r is less than b, right? We haven't shown that yet. And so one thing we can do is we can assume towards contradiction. So I'll write it here. Assume towards contradiction. That r here is either greater than or equal to b. So if you're confused by the phrase assume towards contradiction, this means that I'm going to assume something, and then I'm going to take the logical steps to show that that type of thing couldn't be possible. So in this case, I'm assuming that r is greater than or equal to b. I'm going to reach some logical contradiction, and that means that I will show that it wouldn't be possible for r to be greater than or equal to b. So r must be less than b. And then we'll finish the theorem. So let's see what we have, what we can think about. So if r is greater than or equal to b, this means that r minus b is greater than or equal to 0. What is the e written backwards called? Oh, thank you for asking. That is a good question. That is referring to the existence of something. So I will go back and, like right here, this is saying that there exists a q and an r in the integers. Right, because I'm not showing that there have to be a ton of different possibilities for q and r. I just want to see, like, can I find just one example? Okay, and I see that someone has answered the question in their response. So hopefully that is helpful. If you are still confused, though, please let me know, and I'll try to come up with another explanation. But yes, in general, please ask questions if you're confused, because that's really helpful for letting me know what is being understood and what is not being understood by the people watching. Okay. Back to the proof, we have r is greater than or equal to b. So r minus b is greater than or equal to 0. Well, r is equal to a minus bq, right? So a minus bq, right, which is r, minus b is greater than or equal to 0. But of course, a minus bq minus b, right? We can factor the b out. So we get a minus b times q minus 1. And this is greater than or equal to 0. But remember, that r minus b, right, because b is positive, so r minus b is certainly less than r, right? Because b is a positive. If you take a number and you subtract a positive from it, then you're going to decrease it. So r minus b is less than r, and it's strictly less than, because b can't be 0. Thus, we have a minus b times q minus 1, right, must be less than r, because again, this here is equal to this, which is equal to this. So this just naturally follows from r minus b is less than r. However, q is an integer, so q minus 1 is an integer. So this a minus b times q minus 1, this is an element of the set S as defined above, right? And if we go back, we see S's elements of the form a minus bx for some integer x. In this case, the integer is q minus 1. But hang on a minute. We have an element that is smaller than r. So this right here is the contradiction, because we said that r was the least element of x, or of S, right? Least element of S. But we have an element that's in S, but is less than r. So this is our contradiction. Therefore, r is less than b. And we showed that 0 is less than or equal to r. We showed that already, because members of S are greater than or equal to 0. And r is less than b. And by definition of r being an S, we know that a is equal to bq plus r. Which means we have shown our proof. And I'm just going to fill in a little box here. This is kind of a classic mathematician's thing to do. To show that the proof is complete. So I believe this wraps up the first part, or I guess the first theorem that I wanted to show. So I'll just put a little check next to that part. Before I move on, I want to see, are there any questions? Are there any points of confusion? And what I might do is I might move on. I know there's a delay, so I'll wait a little bit. I see. I'm looking at the video. I'm looking at the video on another device. So I'll just make sure that there aren't any specific questions. But if there are, please feel free to ask and please feel free to interrupt. But then I want to move on to the next part. Okay, so I will state the next part, which I will call Theorem 2. I'll just have like this. So we know, right, that A equals BQ plus R, as in Theorem 1. Thus, I want to show that Q and R are unique. Essentially, I want to show that we know that there exists integers Q and R. I want to show that if we find one solution, then that is the only possible solution. And again, A and B are given, right? So let's go on to the proof of this. So we have So we know that A equals BQ plus R from Theorem 1. And let's suppose that there are two different solutions, right? So let's just suppose, I'll just abbreviate it like that, that R and Q and R prime, Q prime are solutions. Okay, so we have this. What does this tell us? Well, we know that A is equal to BQ plus R in both cases, but we also know that A is equal to BQ prime plus R prime. Okay, I was worried about that. So BQ plus R is equal to BQ prime plus R prime. So where do we go from this? Well, we can kind of isolate the Q and the Q prime and the R prime, right? Because we have BQ minus BQ prime is equal to R prime minus R. And of course we can factor the B out. So we have B times Q minus Q prime is equal to R prime minus R. Okay, great. So I do want to take a little side note from here and note the following, because I believe this will be important. We know that 0 is less than or equal to R, which is less than B. And 0 is less than or equal to R prime, which is less than B. And again, we know this from Theorem 1. So what can we do with this? Well, we see this R prime minus R. So perhaps there's some way that we can combine this R and this R prime right here, such that we can kind of make a nice inequality out of it. So what can we do? Well, some nice properties about inequalities is that we can multiply this by -1, but then we flip the signs. So what does that mean? That means that 0 is greater than or equal to -R. Because again, if R is positive, or if R is non-negative, right, then the negative version of that will be non-positive. So 0 is greater than or equal to -R, and for similar reasons, -R is greater than or equal to -B. And maybe we'll rewrite this one at the top. We'll just kind of switch the order, just so this looks better. And I'll just write a line there. We have B is greater than R prime, which is greater than or equal to 0. And so something we can do is we can add these inequalities together. And so what result does that give us? Well, we get 0 plus B is B. And then -R plus R prime. So B is greater than R prime minus R. And then we add up the right side, -B and 0. So this is greater than -B right here. And you might be wondering, and this was something I was wondering when I was going through this, was how do we know, right? We're adding up these inequalities, and often like we'll add up equations, and I won't necessarily explain like why that's true. I think that's a little bit, I guess maybe kind of a prerequisite, I think, to trying to understand these things. But we do see that the greater than or equal to goes away, and the greater than or equal to goes away. And maybe I'll just kind of do a kind of a side example here. Let's say that we have x is greater than or equal to y, and z is greater than w. Or actually, I'll go the other way around. But it doesn't matter. This is just one case, and I'm going to explain this. This is less of a proof, but more of kind of an intuitive explanation for why this is true. If z and w are equal, well, of course, x plus z will be greater than y plus w, because z and w are the same. I'm adding the same thing to both sides, so the inequality will be preserved. However, if z is greater than w, well, of course the inequality will be preserved, because I'm adding a large thing to x and a small thing to y. X is already greater than y, so I'm just increasing the distance that is between x and y, in a sense. Okay, that was a little side note. If there are any questions, do not hesitate to ask me, but hopefully that kind of clears up any confusion, if there was any. But we go back here. We see that this difference is greater than negative b, and it's less than b. But remember, r prime minus r, if we go up, oh, r prime minus r is equal to b times q minus q prime, right? That's what we showed earlier. So we have, oh, I want to go back to blue. We have b is greater than, well, b times q minus q prime is greater than negative b. Okay, well let's hang on for a second. B is non-zero, right? So we can kind of divide by b on all sides. Kind of a clever thing we can do. Again, we can divide by a positive number, and we do not have to flip the inequalities. So we get 1 is greater than q minus q prime, which is greater than negative 1. So think about this. Q is an integer. Q prime is an integer. So q minus q prime is an integer. Right? This kind of symbol here is an element of the integers. But let's think about a number line, right? Because basically we're saying that there's an integer between negative 1 and 1. So this integer is negative 1, this integer is 1. Well, how many integers are there between negative 1 and 1? There's exactly 1. It's 0. Right? Thus, q minus q prime is equal to 0. Q minus q prime is equal to 0. Well, know what I was trying to do. So q, therefore, is equal to q prime. Well, this is great, right? So now we have, remember at the very beginning, we had bq plus r is equal to bq prime plus r prime. Well, we know, right, that q here is equal to q prime. So BQ plus R, now we'll make the substitution. BQ plus R prime. And now if I subtract BQ on both sides, this gives us R is equal to R prime. So what does this mean, right? This means that if we have two solutions, right, if Q and R and Q prime, R prime are solutions, that's just a little abbreviation. If Q prime and R prime are solutions, then Q is equal to Q prime and R is equal to R prime, which means that there's really only one solution, right, to A equals BQ plus R. Oh, and let me fill in the box, because we have done this. But I kind of want to give an intuitive idea for why this makes sense, right? Because we're saying that A divided by B is equal to Q, right, some quotient, plus the remainder, plus R over B. Right? I did this by dividing B on both sides, as I did earlier. And again, we see this thing here is between, I'll just write it like this. 0 is less than or equal to R over B, which is strictly less than 1. Right? Because if this were 1, then we could just add it back up. And this would be an integer or a rational number. So, and again, right, it makes sense that there's always exists kind of a remainder when we do division, right? Because when you divide, there's always going to be something to the end of the decimal place. And it makes sense that this remainder is unique, because it wouldn't make sense to have multiple remainders when we do division. And the idea is kind of showing that if we assume what addition, subtraction, and multiplication are, that the idea of division is well defined. And so let's say we were back in the day with no calculators and you wanted to explain to someone what division was. And like, what did it mean symbolically to do division, right? That this here is what it means. So this ends up being pretty nice. And we've shown the next part of the division algorithm. I'll just kind of put this here. There's not really enough room for a check mark, but hopefully that's clear. Okay, so now time for a corollary. I'll just call it Theorem 3. Also, again, this was like a huge thing, the division algorithm. So I appreciate you for listening to the proof. And if you have any questions, please let me know, because this stuff can be confusing. Okay. That being said, we're going to move on to Theorem 3. Ooh, let's see if I can write a better 3. There we go. So, I'll start it this way. Let n be a member of the integers. Then n is odd or even, but not both. And I know you might be looking at this theorem and you might be thinking, Mark, this is really obvious. Of course integers are either odd or even and they can't be both. But like, again, if we're starting from the foundations of the integers, right, how would you explain that to someone? What if someone was being really annoying about it and they really want you to convince them? So let's think about it this way. So here's our proof. first of all, what is an even number? So I'll kind of denote the even numbers with this kind of cool E notation. So even numbers are integers of the form 2k, where k is also an integer. And again, that makes sense, right? The even numbers 2, 4, 6, right? 2 is 1 times 2, 4 is 2 times 2. And it works for the negatives as well. -2, -4, those are even. So great. What are the odd numbers? And maybe I'll denote this like O with a little squiggle. Odd numbers are integers of the form 2k plus 1. Right, again, such that k is an integer. And so let's think about it. Right, remember, if we remember the division algorithm, right, theorems 1 and 2 that we just showed, right, A, or I guess in this case, n is equal to b, and let's say we selected a positive integer b. N is equal to bq plus r, right? Where 0 is less than or equal to r is less than b. And r is unique. Right? And we know this is true for all positive integers, right? So for all, and maybe I'll use this symbol here, for all b greater than 0, where b is an integer. This symbol here means for all, and that's, so it's kind of the upside down A. Okay. So what if b is equal to 2? Okay, well then we have n is equal to 2q plus r, where 0 is less than or equal to r is less than 2. Okay, well let's think about this, right? If r is an integer that is less than or equal to 0, or greater than or equal to 0, but strictly less than 2, that means that r is an element of the set, which is 0 and 1. Right, because 0 and 1 are the only integers that meet this property, right, that are greater than or equal to 0 and strictly less than 2. So thus, n equals 2q plus 1, or 2q plus 0, which of course is just equal to 2q. So n is either equal to 2q plus 1, or it's equal to 2q. So n is in the even numbers, or n is in the odd numbers. And you might be wondering, okay, but could n be both even and odd? Like, could that even be possible? Like, how would we show that? And we see that, like, this obviously couldn't be possible. Because, I guess I shouldn't say obviously. From the division theorem we've showed, this can't be possible because the remainder is unique, right? If r equals 1, there isn't any value q that we could select to make r equal 0, and vice versa. If r is 0, we couldn't find another q to make r equal 1. So we use both of these theorems to show that n is either an even number or n is an odd number. But n cannot be both even and odd, right? So we use the existence to show that n could be even or odd, and we use the uniqueness to show that n cannot be both. All right, and thus completes this proof. And I called this a corollary because I felt like this was kind of a direct application of the division theorem, but it's another theorem, another statement that I wanted to prove. And this wraps up part 3, so I'll just mark that right there. And we move on to step 4. So Theorem 4, and I just want to make sure that I have this right. Yes. I wish I were both even and odd. Well, you know what? Maybe one day. You never know. Maybe you could join a numbering system that will let you be both even and odd. That would be nice. So we have Theorem 4, which states the following. N squared is odd implies n, actually I don't want to say n squared is odd. N squared is even implies n is even. Right? For all n in the integers. So basically, if we have, if we take an integer and we square it, and then that thing that it was squared turns out to be even, then the integer itself must have been even in the beginning. So how can we prove this? Well, I'm going to introduce something called the contrapositive. This is kind of a term used in logic, basically saying that P implies Q means that not Q implies not P. So we could prove this using something called a truth table, which I think, I mean, that would be really rigorous, and I do think that's interesting. But I think a better explanation might be kind of thinking of an example. An example I like to think about is, if it is raining, then the ground will be wet. So what's kind of an equivalent statement of that? So we say, if it is raining, then the ground will be wet. Well, if we say that the ground is not wet, then we know that it's not raining, because if the ground was not wet and it was raining, that would make the original statement false. So thus, we have P implies Q means the negation of Q implies the negation of P. So what do I have here? I have n squared is even implies n is even. So what is the contrapositive of that statement? And maybe I'll give you like a few seconds to guess if you want to type it. You can type it in the chat below. I won't be able to confirm here, just based on the delay. But yeah, I'll like count to like 10 or something. Hopefully, given the time that I have been talking, this will give you enough of a chance to make a guess of what would the contrapositive, what would be the logically equivalent version of the statement to prove. Okay, I'm going to start writing. So it is equivalent to show. Okay, n squared is even implies n is even. So n is even. What is the opposite of n being even? Well, again, if n is not even, then it must be odd, right? Because every integer is either even or odd, but not both. So n not being even means it must be odd. So n is odd implies n squared is odd, right? Because the negation of n squared being even, similarly, is n squared is odd. Okay, so how the heck can we show this? Well, let's think about this. If n is odd, then there exists a k in the integers such that, I'm using st as an abbreviation of such that, by the way. There exists a k in the integers such that n is equal to 2k plus 1. Okay, so what is n squared? N squared is equal to 2k plus 1 squared. So we can FOIL this out, right? We get, oh man, I already started wrong. 4k squared is equal to, no, oh my goodness. Okay. We have 2k plus 1 times 2k plus 1. This is 4k squared plus 4k plus 1. Yeah. Okay. So we have this right here. And then we can do is we can factor out a 2 out of both of these. So 2 times 2k squared plus 2k plus 1, right? These two things are the same. But hold on a second. This right here, is an integer, right? Because we're just multiplying and adding integers together. Which means that n squared is odd, right? Because it's 2 times an integer plus 1. So n squared is odd. So thus n being odd implies n squared is odd. We use the contrapositive to show that n squared being even implies n is even. And thus we have reached the end of this proof. And we're going to see why this is helpful coming up shortly. Okay. So, I'm sorry. We have Theorem 1.4 is done, which means we have reached the final step, Theorem 1.5, which I have named, which says that the square root of 2 is irrational. So yeah, this is pretty exciting. Wait, I want to write it like this. Theorem 5. The square root of 2 is not rational. And this is kind of, again, this is kind of the slash through the in symbol means it's not in irrational numbers. Okay, so let's start this this proof. So first of all, what is square root of 2? Square root of 2 is the number, the real number, that when you square it, it equals 2. So I'm just going to assume that that exists. I don't know if there's a specific way to show it exists, but I'm just going to kind of assume that it exists. First of all, if you were to type on your calculator square root of 2, and this might be interesting just to kind of see what happens. We have the square root of 2 is equal to 1.414213562, and so on and so on and so on and so forth. And again, like, it doesn't look like there's a pattern, but we want to like show it rigorously, right? And again, the other arguments that I've used throughout this live stream have been trying to show this idea rigorously. So let's see what we can do. And what we're going to do is we're going to assume towards contradiction again, as we've done in previous proofs. So assume towards contradiction. That square root of 2 is equal to a over b for a, b in the integers, right? So for some a, b in the integers, square root of 2 is equal to a divided by b. And there's one more thing. And the greatest common divisor, right, the GCD of a and b is equal to 1. Now I realize I haven't introduced the concept of the greatest common divisor, but basically a divisor means that that the integer is divisible by it. So for example, even integers are divisible by 2, so 2 is a divisor of even integers. And odd integers are divisible by 1. But like 3 is divisible by 3, 9 is divisible by 3, 20 is divisible by 5, for example. So the greatest common divisor is just the largest integer, and specifically positive, but that's kind of implied with the largest. The largest integer that divides both a and b. And so why would it be possible, right, to just kind of assume that square root of 2 can be written this way, with a and b being co-prime, where co-prime just means GCD of a and b is 1. Well, let's kind of think about it this way. And this is just one example. If GCD of AB is D, which is specifically greater than 1, then we have A over B, which is equal to, well, A is divisible by D, right? So we have dk1 over dk2. But of course we cross out, we can cross out the d, right? We can just kind of cancel it out. Because d is not 0, right? It's greater than 1. And this is equal to k1 over k2. Right, but a is not equal to k, and b is not equal to k2, so we need a new fraction. So essentially, if their divisor is not 1, then we can, and we can keep doing this, right? If the GCD of k1 and k2, for example, is not 1, then we can do this process again. But of course, we can't do this process infinitely long, because there are only so many divisors a number could have. And I guess there is more subtlety. I could show something called the Euclidean algorithm. Well, kind of. But hopefully the point is that like the integers are going to get smaller and smaller. And that's kind of implied. Maybe that'll be kind of an exercise. Yeah, I'll leave that as an exercise if you want to really justify why this is true. But this is kind of the starting point. So, okay. Back to the main idea, we have square root of 2 is equal to a divided by b, and GCD of a and b is equal to 1. Great. So let me write this here. Square root of 2 is equal to a divided by b. And then we can square both sides, right? We multiply each side by itself. So this is an implies arrow, just saying like this first statement implies the second statement, right? That square root of 2, or that 2 here specifically is equal to a squared over b squared. And then this implies that b squared times 2 is equal to a squared. Okay, so what's going on here? Well, a squared's even, right? Because b squared is an integer. So a squared is equal to 2 times b squared. So a squared is even. But remember, by the previous theorem, by Theorem 4, this implies that a is even. And I'll write this here, just kind of as a note. By Theorem 4, well, a is even. So a is equal to 2 times k1 for some k1, for some k1 in the integers. Right, because a is even. So a is equal to 2k1. Right, that's what I showed. N squared is even implies n is even. Yes, so a squared is even implies a is even. Okay. So 2b squared is equal to 2 times k1, this whole thing is squared, right? Because a is equal to 2 times k1. Okay, 2 times b squared is equal to 4 times k1 squared. I just distributed this 2 over. This is a property of exponents. Okay. We can divide both sides by 2, right, to get b squared is equal to 2 times k1 squared. But this means that b squared is even, right? And like I showed, a squared even implies a is even. B squared being even implies that b is even. And so I won't write the whole thing here, but it's the same argument as a being even. So b is equal to 2 times k2, where k2 is an integer. So we have 2 times k2. Well, actually, okay, well, sure, okay. 2 times k2 equals 2 times k1 squared. But really, the main point is a divided by b is equal to 2k1 over 2k2. Oh, but wait a minute, they're both even. Which means that a and b have a common divisor of 2, right? The GCD of a and b is at least 2, right? It could be greater, but it's at least 2. So the GCD of a and b cannot be 1. This is not possible. This is a contradiction. All right. Thus, the square root of 2 is irrational. And that completes the proof. Okay, that's filled it in. So, I don't know, I think this is fascinating that we can start from number theory axioms, and we can show pretty quickly. Right, this was just a little over an hour. That the square root of 2 is irrational. And the thing is, this didn't require us calculating what the last digit of square root of 2 is. I mean, of course, there is none. Right? This didn't require any fancy technology, any graphing. Right? This was just kind of some number theory computation. And we were able to show it. It's possible to show it without even having to think about a number graph. And so I think that's really interesting. And the main point is that there's a lot of these numbers that kind of fall between like the holes of the rational numbers, right? And sorry, I just saw your comment. Yeah, thanks so much. Anyways, if there are any questions about this process as well, please let me know. I know there is a little bit of a delay, so I will wait a bit. Maybe, I don't know, maybe if there are other questions, I might take other questions. We'll see. This was a lot, though, just because this is a whole hour. I know, like, if you have a class that's like an hour long, you probably want some sort of break. But please let me know if you liked it, or if there are parts you didn't like. Let me know your feedback. Let me know what you'd like to see in the future if you want to keep seeing live streams like this. Let me know, I guess, if there's a specific time that you guys want. I'll probably find another day around 4 next week to do the next part. And yeah, maybe, here's what I'll do. I'll give a preview of the next part. Yeah, so here's kind of a sneak peek. So if the square root of n is not an integer, so for example, right, the square root of 4 is an integer because square root of 4 is 2. Square root of 16 is an integer because square root of 16 is 4, for example. But let's say it's not an integer, then the square root of n is also irrational. This is kind of my next goal I want to get to, but we're not there yet. I'll have to do another stream because there is a lot of kind of, I guess, machinery, if you will, to be able to get to that point. Yes, also, I have a Discord. Some of you watching it are in the Discord, and so perhaps are people who are in the Discord, are they allowed to supply or not supply, are people who are in the Discord able to invite people? If you're like not like, can you just invite people in general, or is that something I have to do? Maybe that's something Jules can do, because I know you're a little more savvy with that. Also, like I want to make sure I can still watch the stream and watch the questions. Actually, yes, this is something I'm going to. Here's what I'll do. That was too much. Can I undo that? Can I? Oh, there we go. Oh, Jules said that they should be able to do that. Okay. Okay, now I'm just messing around with this is not my, oh no, encoding overload. I really hope this doesn't like crash or anything. Okay, wait, Jules, can you like put a link in the, can you put like an invite link so people who can, oh my god. Or can someone please put an invite link into the, to the Discord? I would very much appreciate that. I can do that as well. I don't want to. Okay. I'll just do it because. Anyways, but the point is, if there are any more questions that people have, I would really appreciate it if you just want to put that in the chat. Okay. How do I invite people? Okay. You know, I'm wondering if people just aren't putting the invite link. Okay, I have to be honest, I am very new to using OBS. Okay, I just put it in the... Okay, I realize I just beat people to it. Okay. No, that should not... Okay. Someone said something about OBS. If someone has a good tutorial recommendation for OBS, I would appreciate that. Maybe put that in the chat or send it to me. Stream set, yes. Yes, indeed. Okay, I'm going to wait until 5:30. I guess I'll just talk if people have questions, things that they want to talk about. And then if it doesn't seem like there are any questions or any concerns, in about 7 minutes, I'll end it. But I figure I'll leave it open for that amount of time, and then anyone who wants to do something or ask something, or I don't know, you can like put in the chat like how's your day going, or your week. I know people on the quarter system just had finals. If you're in college, if you're on the semester system, then you probably still have a ways left to go. And if you're not in college, if you're in high school, or if you're after, or you're before, I think we had a 7th grader in the audience. I don't know if he's still watching, but I thought that was very cool. Oh, and make sure to like the stream. That's really important, and subscribe. Because if you subscribe, then you'll get notified. I believe there's a bell also. I'm not really sure what that does. DaysX, thank you so much. That's really appreciated. I really enjoyed being able to present this, and I'm really glad that you enjoyed watching it. Hopefully I pronounced that correctly. Also, I don't know if I know you, then I'm sorry I don't know. Yes, please smash that like button, guys. And subscribe as well, because that's how you really get notified. Okay, someone said they're going to have a test on convergence divergence series. Yeah, well, I mean, yeah, I wish you the best of luck. Hopefully you've been able to understand that material. I would like to do some videos in the future about convergence and divergence. I think that'd be really cool. And it will come up for one of these videos in the future. You can probably guess which one of these has to do with the series for an irrational number. But yeah, I mean, the convergence divergence stuff can be confusing. So yeah, I hope it goes well. And yeah, let me know. Which school do... Oh, okay. I guess I don't. I'm not sure. I'm not sure if I want to say. I'm in the United States. I don't know. I just feel like that's a little too much that I'm comfortable with. But yeah, I mean, I don't know. If you guys want to share, like, that's fine. That's just kind of the me thing. But yeah, no, I think this is really cool. Thank you guys so much for watching. Again, I have a Discord. So please make sure to join that. And there's all sorts of community discussion that we can have. Oh, very cool. Yeah, no, I know I had a lot of Canadians. I have people from University of Toronto, which I think is really cool. Yeah, hopefully Canada is holding up well with COVID stuff. I haven't really been following that. But yeah, yeah, I don't, I guess it seems like the stuff I do in this channel is relevant to the U of T curriculum. So I think that's very cool. Yeah, I don't know. I don't have much planned, but like I said, I'm just gonna keep this going until 5:30, and then I will end the stream. Oh, and if someone has recommendations for like more stuff, how to do OBS, I would love to see it. I should visit U of T when this is all over. If all of my oh my goodness. Are you guys all math majors? Or I don't know, like are there like obviously if there's other majors that involve this stuff, probably like computer science and engineering or physics even. I don't know. I don't know how long the delay is. Okay, there seems to be disagreement on whether or not Greg Sherman goes to U of T. I couldn't say I do not go to U of T. But yeah. Hey, well that's cool as well. I know there's a lot of math concepts involved in CS. And like you probably have to take math classes anyways. And of course, like it's really cool that these kind of ideas about irrationality, like, and stuff that's like really abstract, does have direct applications. Oh, physics. That's very cool. Yeah. Yeah, I mean, it's so, I guess there's gonna be a lot of people from different backgrounds. Or, who are going to be going into kind of different perspective fields. Okay. It is almost 5:30, so I will be closing out the live stream in under a minute. But yeah, thank you guys so much for watching. Make sure to like, subscribe, join the Discord. And yeah, all questions can be put on there, or if you're not watching this live, you can please feel free to leave a comment. And yeah, that sounds great. Have a wonderful day.